Welcome to our deep dive. Today we're going to be tackling something pretty fundamental: gravity, friction, and forces.
Oh yeah, these are the real movers and shakers of the universe.
Exactly. And we've got a whole bunch of sources to dig into: physics textbooks, real-world examples. We even threw in a nod to that article about the Parker Solar Probe that you sent me.
It's gonna be fun.
So where do we even begin with something as big as, like, all the forces in the universe?
Well, I think a good place to start might be with something we all experience every day: gravity.
Okay, gravity. I gotta admit, I kind of take it for granted. What goes up must come down, right?
Sure, but have you ever stopped to think about why things fall down in the first place?
Hmm. Not really.
It all comes down to this force of attraction between any two objects that have mass. And when I say any two objects, I mean any two. You, me, this table, the moon, even a tiny little grain of sand.
So there's like a gravitational pull between, like, me and my coffee cup right now.
Technically, yes. The Earth's mass is so much greater that its gravitational pull just completely overwhelms anything else.
That makes sense. But if gravity is pulling on everything, why don't we all just, like, clump together into a giant cosmic ball?
That's a great question. It turns out the strength of gravity depends on two things: mass and distance. The farther apart two objects are, the weaker that gravitational force is between them.
Oh, okay. So, like, the sun is supermassive, but it's also really far away.
Exactly. And speaking of the sun and things orbiting around it, remember that article you shared about the moon?
Yeah, I was always curious about that. Like, how does the moon just stay up there? Why doesn't it fall down?
Well, it is falling, but it's also moving forward at the same time. And it's moving forward at just the right speed to perfectly balance out the Earth's gravitational pull.
So it's like it's constantly missing the Earth.
That's a great way to put it. And that's what we call an orbit, a continuous fall that never actually ends. And it's not just the moon. All the planets in our solar system are doing the same thing around the sun.
Wow, that's mind-blowing. It's like a perfectly choreographed cosmic dance.
Exactly.
So speaking of choreographing things in space, you mentioned the Parker Solar Probe. Didn't that got insanely close to the sun, right?
Oh, yeah. That mission was only possible because scientists have a really good understanding of gravity. I mean, they use Newton's law of universal gravitation to calculate the probe's trajectory with incredible precision. So it was able to get close enough to study the sun's atmosphere without getting pulled in by its gravity.
Wait, Newton's law? Isn't that the one about the apple falling from the tree?
Yep, that's the one. But it's so much more than just apples. It's a fundamental principle that governs the motion of everything in the universe. From falling apples to planets orbiting stars, even to probes flying past the sun.
It's hard to wrap my head around that. Like, the same law that explains why my pen falls to the floor also explains how we can send a probe to the sun.
I know. Physics is pretty amazing.
Okay, so Newton's law helps us understand how gravity works, but then there's also something about Einstein and gravity, right?
Yes. We can't talk about gravity without mentioning Einstein. He came along and basically turned our understanding of gravity upside down. See, instead of thinking of it as a force, he reimagined it as a curvature of space and time that's caused by massive objects.
A curvature of space and time. I'm not going to lie, that sounds pretty out there.
I know, it's a lot to grasp, but there's a helpful analogy we can use to visualize this. Think about a bowling ball on a trampoline.
Okay, yeah.
The bowling ball creates a dip in the trampoline, right? So if you roll a marble across the trampoline, instead of traveling in a straight line, it'll curve around that dip created by the bowling ball. That's kind of like how gravity works according to Einstein. Massive objects like stars and planets, they warp the fabric of space and time around them, and other objects just follow those curves.
So it's not really a force pulling things together, it's more like the shape of space-time itself that's guiding their paths. Okay, so we have Newton's law, which is great for understanding a lot of everyday things, and then we have Einstein's theory, which is more for extreme situations like black holes.
Right. And it's important to remember that both of these ideas have a place in our understanding of the universe. They work together to give us a more complete picture.
This is all really fascinating, but it does feel a bit abstract, you know? Like, how does this actually play out in our everyday lives?
Well, think about something as basic as walking. When you take a step, you're pushing off the ground with your foot.
Right.
But without gravity, that push would send you floating off into space.
Oh, I never thought about it like that.
Gravity is literally keeping us grounded.
Literally.
And it's not just about keeping our feet on the ground, it's also responsible for things like the ocean tides and the formation of stars and galaxies.
So gravity's a pretty big deal.
Gravity's a very big deal. It's one of the most fundamental forces that shapes the universe as we know it.
Wow. Gravity is way more complex and way more interesting than I ever gave it credit for.
Yeah, it's pretty incredible. Now, let's shift gears a bit
Hmm.
and talk about another force that's constantly at work. Force itself.
Okay, so force is like any push or pull. Like when I push a shopping cart or lift a weight.
Exactly. Anytime you see a change in motion, you can bet there's a force involved. And what's really neat is that force is a vector, which means it has both size and direction.
So it's not just how hard you push or pull, it's also which way you're pushing or pulling.
Precisely. Think of it like giving someone directions. You need to tell them both how far to go and which way to go.
So force is like an arrow pointing in a specific direction, and the length of the arrow tells you how strong the force is.
You got it. And we measure force in units called newtons, named after, you guessed it, Sir Isaac Newton.
Newton is everywhere.
He was a busy guy. Okay, so now things get really interesting when we start talking about multiple forces acting on an object at the same time. We call that net force.
Net force, so that's like the overall effect of all the pushes and pulls going on at once.
You got it. Imagine a book just resting on a table. Gravity's pulling it down, but the book's not falling through the table, right?
Right.
That's because the table is pushing up on the book with an equal force. These forces are balanced, so the book stays put.
So balanced forces equal no movement. What about unbalanced forces?
That's when things start to move. Think about a tug of war. If both sides are pulling with the same force, the rope stays in the middle. But if one side pulls harder, the rope moves in their direction.
So it's all about who's pulling harder.
Exactly. And sometimes that push and pull involves a force that we often think of as working against us, and that is friction.
Ah, friction. I remember reading about that in one of the articles. That's what makes it so hard to push furniture across the floor.
Right. Friction is the force that opposes motion between surfaces that are touching. It's everywhere, and it can be both helpful and a nuisance.
Helpful like when it gives us grip to walk without slipping, but a nuisance like when it wears down the tires on our car.
Exactly. And at a microscopic level, friction is caused by tiny bumps and valleys on surfaces interlocking and resisting movement. Even surfaces that seem smooth to us have these imperfections.
So it's like trying to slide two pieces of sandpaper together.
Perfect analogy. Now, friction comes in a few different types. We have static friction, which is what keeps things at rest, like your shoe gripping the ground before you take a step.
And then there's sliding friction, which happens when objects slide over each other, like when you do firmly push that furniture across the floor.
Exactly. And we can't forget rolling friction, which is actually much weaker than sliding friction. That's why we put wheels on things.
Oh, that makes sense.
And lastly, we have fluid friction. That one applies to objects moving through fluids like liquids or gases.
So a parachute slowing down a skydiver would be an example of fluid friction.
You got it. Each type of friction plays a unique role in how things move or don't move in our world. And speaking of bouncing back, did you see that article about the new materials that they're putting in running shoes these days?
Oh, yeah. It talked about how shoe companies are always trying to find that perfect balance between cushioning and bounce.
Well, that bounce is all thanks to a force we call elasticity. It's the ability of a material to return to its original shape after being stretched or compressed.
Like a rubber band.
Exactly. And this snapping back is due to a force called, you guessed it, elastic force.
It's like an invisible hand that's trying to put everything back in its place.
I like that. And this elastic force is what makes rubber bands, bungee cords, and even springs so usable.
Springs. They're everywhere. In our cars, our mattresses. I even have an old school scale that uses a spring.
Exactly. They all rely on that elastic force. It's amazing how something so simple can have so many applications.
It really is. So to recap, we've got gravity keeping us grounded, friction pushing back against us at every turn, and elasticity making things bounce back. It's kind of
Right.
wild when you think about it.
It is, and it's all happening around us constantly.
It really makes you see the world a little differently, doesn't it?
Absolutely, and we've only just scratched the surface of what there is to learn about these amazing forces.
It's like elasticity has this amazing ability to reset things back to how they were.
Yeah, it's this fundamental property of certain materials, and we use it in so many ways.
Oh, absolutely.
Like you mentioned running shoes earlier, and the midsoles of those shoes are made from materials that have a lot of elasticity. So when your foot hits the ground, the material compresses to absorb the impact.
And then it springs back to give you that extra push forward.
Right, so it's like having these tiny little trampolines under your feet with every step.
I love that analogy. So the material they use in the midsole That actually makes a big difference in how the shoe performs, right?
Oh, for sure. Some materials are better at absorbing shock, while others are better at returning energy. Like, it's a constant game of trying to find the perfect balance, and shoe companies are always coming up with new materials and designs.
It's amazing how much science goes into something as seemingly simple as a running shoe. And you mentioned that elasticity plays a huge role in engineering as well.
Oh, absolutely. Engineers rely on the principles of elasticity all the time, especially when they're designing structures that need to be able to withstand a lot of stress and strain.
Okay, so like bridges and buildings, things like that.
Exactly. Think about a bridge for a second. It has to be strong enough to support all the weight of the cars and trucks driving over it,
Right.
but it also needs to be flexible enough to bend a little bit under heavy loads so it doesn't just snap.
So it's like a balance between being strong and being flexible, kind of like a tree that can bend in the wind.
Yeah, that's a great analogy. Finding that right balance is key, whether you're designing a bridge or a skyscraper or even an airplane.
It's incredible to think about how these fundamental physics concepts are being used to literally shape the world around us.
It is. It really shows how interconnected all these forces are that we've been talking about. Like, you can't really talk about elasticity without also thinking about gravity, friction, and all those other players.
It's like a giant puzzle where all the pieces fit together. And speaking of gravity, you said earlier that the acceleration due to gravity is 9.8 meters per second squared, but what does that actually mean in real-world terms?
It means that every second an object falls, it's picking up speed, and it's doing so at a pretty fast rate.
So it's not just about how far you fall, but also how fast you're going when you hit the ground.
Right. And this understanding of acceleration due to gravity is crucial for everything from designing safety features in cars to planning a rocket launch. Like, if you don't account for gravity, things could go wrong very quickly.
So it's kind of a big deal.
It's a very big deal.
Okay, so we've talked about gravity pulling things down, and we've talked about elasticity making things bounce back. But what about friction? It always feels like it's working against us.
Well, friction can definitely be a nuisance, especially when you're trying to move something heavy. But it's also incredibly important for a lot of things that we do every day, like walking or driving a car, even just holding onto a coffee cup.
Oh, that's true. I never thought about that.
Without friction, our world would be a very slippery place, and things would be a lot harder to control.
It would be like trying to walk on ice all the time.
Exactly. And driving, forget about it. Your tires need friction to grip the road so you can steer and brake.
So friction is essential for movement, but it also creates resistance.
Right. It's this constant push and pull. And the amount of friction between two surfaces can vary depending on a lot of things, like what those surfaces are made of, how rough or smooth they are, and how much force is pushing them together.
Right. I remember reading that scientists are always looking for ways to reduce friction in machines, to make them more efficient.
Absolutely. Reducing friction can help machines run smoother, last longer, and even use less energy. And there are all sorts of creative ways to do that.
Like oil and grease, right?
Yep. Lubricants like oil and grease can really help reduce friction. And there are also things like special coatings that can be applied to surfaces to make them even more slippery.
It's incredible how much time and effort goes into understanding and controlling these invisible forces.
It really is. And it just goes to show how crucial they are in shaping our world, even if we don't always realize it.
Okay, so we've got gravity, elasticity, and friction. But we've also talked about how all these forces work together in some pretty amazing ways. Like, can you give us any other cool examples of how that interplay of forces shapes our world?
Sure. Let's take something as simple as throwing a baseball.
Okay, I'm listening.
When you throw a ball, you're applying a force to it. That force gives the ball its initial speed and direction.
Right, so that's the push that sends the ball flying through the air.
Exactly. But as soon as that ball leaves your hand, gravity starts pulling it down.
So that's what creates that nice arc that the ball makes.
Exactly. But it's not just gravity. There's also air resistance, which is a type of fluid friction. And that's working against the ball's motion, slowing it down.
Oh, I see. So you've got the force of your throw, gravity pulling it down, and air resistance pushing back against it. It's like a three-way tug of war.
That's a perfect way to describe it. And the outcome of that tug of war determines where that ball will land.
Wow, this is fascinating.
Yeah.
I never thought about how much physics is involved in something as simple as throwing a ball.
And it's not just baseball, of course. This interplay of forces is happening all around us all the time, from the motion of planets to the flight of airplanes to, like you said earlier, how our own bodies move.
It really makes you appreciate just how complex and interconnected our world is.
Yeah, absolutely.
Speaking of the complexity of nature, there was one article you sent that talked about how scientists are studying friction to create new materials that, get this, can mimic a gecko's ability to climb walls.
Oh, yeah. Geckos have these tiny little hairs on their feet called setae. And these setae create something called van der Waals forces, which are basically these super weak attractions between molecules.
Okay, so it's not just that they have sticky feet, it's that they're able to harness these tiny, invisible forces.
You got it. And by figuring out how those forces work, scientists are hoping to develop new things like adhesives and robots that can climb walls, even things like new types of medical bandages that stay in place without irritating the skin.
It's amazing how, by studying these seemingly basic forces, we can come up with such innovative solutions to real-world problems.
It's a testament to the power of scientific inquiry.
It really is. It's
Yeah.
like the more we learn about these fundamental forces, the more possibilities open up.
Absolutely. And who knows what other incredible discoveries are out there just waiting to be uncovered.
It really is amazing how much impact these tiny forces that we can't even see have on our world.
It just shows you the power of really understanding the fundamentals of how things work. Once you understand those basic physics concepts, you start to see them everywhere.
Oh, totally.
It's like you've suddenly got this new lens to look at the world through.
Exactly. And, in one of those articles I sent you, there's this fascinating bit about how scientists are actually using the principles of friction to develop new earthquake-resistant buildings.
Oh, that's right. That's such a cool example of how we can take our knowledge of these forces and use it to create structures that are, safer and more resilient.
Yeah, it's like they're designing buildings that can actually roll with the punches, so to speak.
Yeah, exactly. By incorporating certain materials and design features, engineers can make buildings that are better at absorbing and dissipating the energy from an earthquake, which can really help to minimize damage, and ultimately protect lives.
It's amazing how something as destructive as an earthquake can be mitigated by just, cleverly applying these principles of physics.
Yeah, and it just goes to show that we should never underestimate the power of just basic scientific understanding.
Totally. It really is about pushing the boundaries of what we know.
Absolutely.
And who knows what other amazing breakthroughs are out there waiting to be discovered, right?
Oh, for sure. The possibilities are endless.
Well, and that's what I love about these deep dives.
Yeah.
It's not just about learning facts. It's about kind of sparking our curiosity and, opening our minds to new possibilities.
Oh, totally. It's all about keeping that sense of wonder alive.
Yeah, exactly. And speaking of wonder and possibility, do you remember that article that I sent you about space travel and the challenges of overcoming inertia?
Yeah, I do. It was talking about how much energy it takes to get a spacecraft moving, especially when you're trying to achieve the kinds of speeds that would be needed for interstellar travel.
Exactly. It's like this massive hurdle that we need to overcome if we really want to explore the cosmos.
It is a huge challenge, but I think that a deeper understanding of inertia and how forces work could lead to some pretty big advancements in propulsion systems.
Like what kinds of advancements?
Well, imagine if we could develop new propulsion systems that utilize things like electromagnetic fields or even harness the power of gravity itself. I mean, things that are kind of out there right now.
That would be revolutionary. It would completely change the game for space exploration, right?
It would. I mean, just imagine being able to travel to other star systems to discover new planets, maybe even encounter other life forms out there.
It's mind-blowing to even contemplate. So as we wrap up this incredible deep dive, is there one key message that you want to leave our listeners with?
I think it would be never stop questioning, never stop exploring. Because the world around us is full of wonders. And the more we understand about the fundamental forces that govern it all, the more we can really appreciate its beauty and complexity.
I love that. It's been absolutely fascinating exploring these forces with you today. Thank you so much for sharing your insights and expertise.
Oh, it's been a pleasure.
And to all our listeners out there, thanks for joining us for this deep dive into the world of physics.
I hope you enjoyed it.
And remember, stay curious and keep exploring. Who knows what other amazing discoveries are just around the corner waiting for you to find them?